right, let's get started. So last time we talked about distance functions and how that could be used in the context of classification. So just as a recap, we formulated a classification problem as sort of a regression problem previously, right? So you have a mathematical model that is represented as f, and then the role of this function f is to take in a feature vector x as an input and then produce an output that correspond to the input feature vector. And then the way that we formulated this was we did some trick. So in case where we have the ordered category, we set y to be an integer, right? Maybe well, yeah. So be an integer, positive integer actually. On the other hand, in case where their ordering is not so meaningful, we encoded everything as a combination of a, as a combination of zeros and ones, right? So we call it a one-hot encoding. So recall, one-hot encoding was a representation where, in case we have three classes, we represent them using a probability. So last time we saw the example of dog, cat, and dolphin. So in that case, for each of the rows of the table, you could assign a probability value in terms of the probability of that data sample be in each of those categories. So in the ground truth data set, I mean, in case you have a class dog, then the values are determined to be 0 and 0, meaning that the probability of this row being a cat is 0%, and the probability of this row being a dolphin is a 0%, and therefore 100% this is a dog, right? And then we could have that kind of, this kind of representation as well, which in this case indicates the class is cat because we have 100% associated with the cat. So that was the one-hot encoding. So as a matter of fact, if you have a n+1 classes, the dimensionality of that vector, one-hot encoded vector, was an n dimension. So that was a typical formulation of the classification that we saw last time. And then we introduced this example of IRIS data set. So I show you some slides indicating the plots, across different species of the iris flower. Now, then we went into this, slightly different formulation of K-nearest neighbor. So K-nearest neighbor, recall, the algorithm is based on the previous observation. So when there's a new data point, that's a new observation. So we currently don't know the class of this new observation. And when we have such a new data point, then what we do is to basically find the K-nearest neighbor. So in case of, k equals to 1, what we do is to find the nearest neighbor, which is this pink dot over here. And therefore, since the, classification, the K nearest neighbor, the first nearest neighbor has a classification of, color-coded pink. So let's call it the red, pink dots are, dogs. And then the other yellow dots are cats, so dog versus cat problem. And in that case, since the query point, the gray dot here, is closer to a pink dot representing dog, then the classification of this gray dot is going to be a dog. Similarly, when k is bigger than 1, so let's say in this example, we're assuming k equals to 3. And in that case, we have, 3 nearest neighbors over here within this dashed circle. And if you think about it, 2 of those neighbors are cats, and then only one of them is a dog. So if we take the simplest principle of just taking the majority vote, then the classification of this gray dot is going to be cat. So then the dot is going to be color coded as yellow. So that's simply the idea of K-nearest neighbor algorithm. So typically it's not stable to use k smaller than 6. 6 is roughly kind of the number that when you go below 6, then it can be quite sensitive to noise, because for example, in an extreme example, if you rely on one nearest neighbor, then if a point happened to be at some location because that point was a outlier, then your chance of misclassifying a new observation is going to be pretty high because it depends only on one neighbor. In case you have a larger number of k, then the stability of the algorithm gets increased because obviously, instead of relying on just one sample, now you're relying on a larger number of samples, and then you're taking the majority vote. So you can make your algorithm a little more robust by doing that. Now, there's a question in the chat, that says, what about 50-50 split in neighbors? Yes, that's a good question. So imagine a case where k equals to, let's say, 4. And in fact, if k equals to 4, I think this used to be a gray dot over here, right? And then if k equals to 4, I think these are the neighbors. And in this case, we have 50-50 split. So first of all, selecting k is important in that sense. You probably don't want to set a number that can result in a 50-50 split, okay? So in a binary classification problem, you obviously want to go with an odd number k. Otherwise, you may end up having, this ambiguous stage, right? So that's one option. However, when you have a multi-class problem, then obviously selecting k in a way that can prevent the tie is going to be way more difficult, and there might not be a k parameter k that is guaranteed to give a tie break all the time. So in that case, what you want to do is, well, there are a bunch of different heuristics. The simplest heuristics that you can apply in that case is just just to draw a dice. So in the binary classification problem, or in fact, in any situation, let's say you have, for a given query point, you have 2 majority votes, and then there are 50-50. Okay, so in that case, you can just roll a dice, and then based on that random selection, you can just randomly select either of these 2 labels. So that's one, probably the simplest heuristic. Other heuristics can be to, add one more neighbor. Okay, so let's say you had, k equals to 4 nearest neighbor, and then it happens to be a tie, a tie between 2 classes. Then what you can do is to check for the 5th neighbor and then see what the 5th neighbor thinks. And then, depending on the class of the 5th neighbor, then you may, reach to a little less ambiguous decision. Yet another heuristic you can apply is to give a weighting factor. So you can give a weight by the distance from the query point. That's another option that you can take. So if you think about it, it is kind of unfair to say, well, and this is not the perfectly good example, but it is not fair to give an equal weight on all those neighbors. You may instead argue that the neighbors that are close to the query point should be weighted more, whereas the neighbors that are further apart from the query point should be weighted less. So simply speaking, you can weight the decision based on the inverse of the distance from the query point. Okay, and if you weight them according to the distance, then numerically, there's nearly 0 chance where you'll have 50-50 split. So those are all kind of different, strategies. And to be honest, those are all heuristics. So, it's really hard to say, which one is better than which one. And there's obviously a trade-off. So if you go with the weighted, the weighting heuristic, for example, then you may be, a little happier because, it gives you a feeling that you're relying on some, mathematical formula as opposed to just, some random heuristics, like the first heuristic that I mentioned, rolling a dice. But you're, doing that by, by compromising the computational speed. If whenever there is a query, if you have to measure the distance and then weight them differently and do extra computation, then obviously that's that can be a meaningful consumption of computational time, as opposed to rolling a dice is just the generation of a random number. And the likelihood of getting 50-50 split is not so terribly high, right? So it's kind of a trade-off between the computational cost and then trying to be more rigorous. what. So there are a lot of different heuristics in that sense, and depending on the problem that you really have to choose a solution that is most suitable for your own situation. So there's no like a single answer to that. But that was a good question, in fact. Okay. All right, so that's more or less what we covered last time. So before to go any further, what I would like to do is to send you guys all to a breakout session, and I'll let you guys to discuss how you would apply KNN to a large data problem. So we just discussed KNN in a general context. We never really talk about the issue of big data or whatsoever. And the algorithm of KNN itself is pretty simple to understand. So I hope everyone understands, what's really going on. Now, I want you to imagine and discuss what kind of strategies could be possible to apply KNN to a large data problem. So to give you a hint, let's say instead of 100 data samples, now you have 1 million data samples. And obviously, whenever there's a new query point, computing the distance from the query point to all the training samples, all the points in your database, is going to be quite time consuming, right? You have to compute the distance from the query point to each of the data samples for 1 million times if you have 1 million data samples. If you have 100 million data samples, then obviously you need to do 100 million times of that computation, which is going to be, quite time consuming. So under this situation, what would be the strategy that you would apply to implement KNN? Okay, so that's actually the first question. Okay, another question is, what if you have a large variety of data samples? So instead of just a single, trait or a single feature, you have multiple different features, and they're all kind of, from different modality, different sensors, different types of measurements and things like that. Then what would you do in case you have a large variety? Finally, in case when you have a data that is growing rapidly, then what would you do to implement KNN algorithm? So again, the situation is you have, let's say, 1 million point at the current stage, but then the data increases. The new data comes in to your database at a pace of 100 samples per second. Okay, so you can easily imagine that your database is going to grow quite significantly. So then whenever there's a query point coming in, you need to compute the distance from the query point to all the data samples in your database, and your database is growing at a pace of 100 samples per second. So in that case, what that means is the reference points are growing at a rate of 100 samples per second, so that you have to compare the distance additionally to those 100 additional data samples per each second. And when that kind of situation happens, what would be your strategy? Okay, so this is kind of an open-ended question, so don't try to guess what the right solution would be. To give you a hint, Apache Spark, for example, does not have KNN, and perhaps they decided that KNN is not suitable for a large data set. Okay, I don't know the background of that decision, but Apache does, Spark does not have KNN implemented in their framework. So my point here is this is a fairly open-ended question, so you don't have to try to guess what the right answer is going to be. So with that, I'm going to put everyone into the breakout room, and then we'll give you about 15 minutes to discuss. So I think everyone is back to the main room. So what was the result of your discussion? Would KNN be suitable for a large data problem? Can you guys drop your answers and thoughts in the chat window? Ooh, I see a big text over there. Okay, so one of the answers in the chat, and I encourage you guys to keep typing. One of the answers in the chat says, first, make a for loop containing all possible values for k and pick the model with the highest test value. And that may not be appropriate for big data analysis because it'll be time consuming to run all tasks. So I guess the idea is to somehow distribute the, well, actually not. So I don't know if I understood the first point, Andy. If you can elaborate on that, that'd be great. The second point was to choose the K based on the industry knowledge. So I guess choose K based on the domain knowledge. And we may lack in the domain knowledge and it may cause bias. Yeah, I mean, even for a small data problem, you probably want to choose K based on a domain knowledge. Always, knowing your problem better is, always the first step before jumping into analyze data. So I think that's something that is applicable to not only just the large data set, but also, small data problems. Divide data set into multiple sections and choose K. Well, I think the idea of dividing a data set into multiple sections is a good idea. So if you think about it, when you have a distributed storage, you may want to actually utilize the power of a distributed data set, right? So, well, you have your database distributed across multiple locations, and let's say instead of having 5,000 rows at one location, you have, let's say, 5,000 rows distributed across 5 data nodes, and then for each of the node you have 1,000 data samples. So in that case, when you have a new query point, instead of comparing it against all 5,000 rows one by one at a single computing core, you can distribute that query to multiple locations and then try to parallelize the distance computation, right? And in that way, what each of the data nodes can do is to maybe, return back, top 5, top 5 nearest neighbors to the data, to the query point. And then the master node is going to then collect top 5 from, all those 5 locations, which is going to be about, only 25. And for 25 rows, you can sort them based on the distance, right? Calculated from each of the data nodes. So actually, the idea of distributed distance computation is quite viable, I would say. Okay, I think that's what Andy meant. Moving on to the other suggestion. Appears a more intelligent classification model than KNN. So I guess what you're suggesting, Daniel, is do something other than KNN. This is actually the answer that is shared by many, experts. So like I said earlier, Apache Spark does not come with KNN library simply because KNN, is not so suitable for large data systems. So in fact, yes, if you can find other classification model, then it is better to use, something else than KNN. We'll get back to this, actually. This is an important point. I'm moving to the next idea in the chat. Split the large data set up into representative smaller sets. Yes, the keyword I think here is representative. So split the data set up to representative small data set and distribute them to slave nodes. And the test value gets sent to each node or set of nodes to run a KNN. The most common response is the classification use, known classification to calculate. So it's more or less the same thing that I was explaining on the screen. But I really like that you pointed out the word representative. Okay, so instead of just randomly splitting the data set into 5 distributed sources, you could actually do a smarter job and then maybe run a clustering algorithm, for example, and then pre-cluster them into based off of their similarity. So for example, what I mean by that is, let me see if I can erase everything. Yeah, there you go. For example, let's say in your data space, imagine you have data distribution that looks like this. So what I'm trying to illustrate over here is a situation where you have lots of data samples that are, in a very small, clustered in a very small location. And then, many of the data points are kind of distributed here and there. In that case, obviously, you probably don't want to have everything over here and then include that in the KNN algorithm. Instead, you can select just a, one or two representative sample from each of the cluster and then use them for doing KNN. Okay, so that's actually an idea of reducing N. If you recall the one of the first lecture slides about supervised learning for big data, we discussed many different strategies, and one of them was to reduce the number of data samples. So obviously, by selecting only a representative sample, then you can effectively reduce the size of N, and you can run KNN on a small subset of the original data set. And then in that way, you can make KNN work on a large data problem. So that's also a viable solution, I would say. There's another thought. This is great. I love seeing your ideas, and so far nothing's wrong, right? So another idea I'm seeing on the chat is to use locally sensitive hashing using hash tables. So yes, this is actually one of the things that we're going to learn later in this lecture. So the idea of hashing is, I don't know, one of my favorite analogy is the how people, librarians classify books and order them and index them and manage them in libraries. So you have lots of data points, right? And you can actually kind of hash them, meaning you can set sort of a section and then maintain them in each of different hashed location. So to be more specific, let's imagine, well, let me just go with a simple case, okay? So this is a data space spanned by two parameters. Let's say, if you recall that family car example, one of the variable was a price, and then the other variable was an engine power, I believe. So you have a two-dimensional space now where you have lots of data distributed here and there, okay? So all of these are data points. And what you could do is to, let me change the color here. What you could do is to, split them into smaller cells, okay? So, what I'm doing is I'm splitting the space into small cells. So that's room, 101. This is a room 102. And this is a room 103. This is a room 104, and then room 105, and so on and so forth. I mean, it doesn't have to be just, like this, but I'm conceptually drawing the partition of the data space into smaller rooms. And for each of the room, let's say you have a list of guests, okay? So maybe, if I use the librarian example, each of the room is where you collect a large amount of books. And then, I mean, if you've ever been to main library, right, they have several rooms, and then depending on the category, the book type and category, you visit a different room, and then for each of the room you have different bookshelves, and then that's basically how you find a book in a library. So it's kind of similar to that. So think of them as like kind of individual bookshelves, right? And then for each of the bookshelf you have a list of all the books, okay? So that's basically the idea of hashing. So then, what happens in practice is that, let's say you have a query point, which I'm going to represent using a green dot over here. And when you have a query point, maybe green was not a best choice of color. Let me change it to blue. Is it better? Maybe. Yeah, so let's say you have a new query point, which is the blue dot over here. Now, what you can do is, first of all, roughly check, okay, which room that this blue dot belongs to, okay? That's the idea of hashing. And if you can do that rough classification fast enough, okay, which is the role of this hash table or hash function, if you can do that fast enough, then you can skip on searching the other locations, okay, data points in the other locations, but limit your search to a certain room that the blue dot belongs to, okay? I'm not going to tell you how, but imagine that there is some way to split the space into, different sections, then, it might be possible actually to find a way to, it might be possible to find where this blue dot belongs among, those many sections. And then only compare this blue dot against the points that belongs to that same section. Okay. So by doing that, instead of searching through this entire data set, you can search only within a small section of the data set. And by doing that, you can, effectively manage the computational burden applied to a large data problem. Okay. So that's another, option you can take in terms of how to, get around the issue of a large data set. Now, regarding that, I guess, the answers that I see on the chat window are mostly about when you have a large volume of data. Now, what if we have a large velocity? Was any of you able to find some convincing answer from your breakout discussion? Well, I don't see much responses in the chat, but continuing on this, we may actually rely on this kind of hash table. That's one of the first strategies that I will, probably use if I have to use KNN on a data set that has a large velocity. So the idea is, whenever you have a new data point, you keep your hash table, and then the hash table is going to be updated with the new, newly sampled data. So those are the new training points, right? And they're going to be added to here and there in the distribute, in the data space. And then, the idea is still the same. Instead of, doing the search over the entire search space, you can limit the search, into a specific section, like what we just did. Now, the problem with a large velocity is that, well, when the velocity increases, then, when the velocity is large, then what happens is the members of each hashed sections are going to increase at a rate that is not so much manageable, right? So whenever new data is added, you still, you probably want to do some sort of a management in balancing the new data with the old data, because your storage is kind of limited and you don't want to just keep all the data and accumulate the entire, data. Otherwise, it'll explode easily. So let me repeat that again. So in case when you have a large velocity, then, the speed of data accumulating is going to be, unmanageable, and it can easily kind of explode, if you just let it accumulate. So you probably want to have some sort of a strategy in terms of how to update the hash table, right? So instead of letting it accumulate and then, squeeze into those rooms, you probably want to, set the maximum capacity for each of the room. And then whenever a new data arrives beyond the maximum capacity, you probably want to replace old data samples with the new data samples, or do some trick to manage maintain the capacity, right? So, you can think of those kind of strategies and still apply this hash table idea for a data set with a high velocity. The other thing is, well, we previously discussed the idea of using, let me try to erase everything here. We discussed the idea of distributed computing. So again, instead of having, everything in one location, if you can distribute that, the new data set into, multiple storage locations, then the slave nodes are going to, for a given query, the slave nodes are going to compute the distance from the query point to, each of the data rows, and then we'll send it back the distance, maybe top 5 or top 3, neighbors to the master node, and the master node is going to just aggregate that and, produce the final result, right? So that, that was the idea of a distributed solution. Now, in the same context, when you have a large velocity, that means, each of the data nodes is going to accumulate a large quantity of data, at a very fast rate, or it may, it may also be true that the number of data nodes are going to increase as you accumulate more data, and then your company invests more money on data storage, and then it increases in every dimension. So in this case, I think the idea is more or less the same, right? Whatever the maximum capacity of each of the distributed storage is, you're going to distribute the search query to multiple locations, and then let them do the comparison on the local, data set, and then, send back the result to the master node, and then the master node is going to aggregate the numbers. Now, those are, some possible strategies in terms of using KNNs in the context of large volume and large velocity. I haven't talked about the variety yet, because that's something I'm gonna talk about later with this hash function idea. But if you think about it, I mean, the more you think about it, the more you realize that KNN is not really for large data sets, right? And that's partly the reason why big data analytic systems like Spark does not support KNN. And it is generally agreed, in fact, by many data scientists that KNN is not, super suitable for big data problems. So for small data problems, KNNs might be, really good. And in fact, KNNs have a really good performance in terms of classification accuracy. So they are usually very good, but when you have a large data set, then you will quickly face the curse of dimensionality and the curse of, large volume. And, despite all this distributed approaches and everything, you may not be actually satisfied with the performance of KNN. Okay, so that is kind of a summary. Okay, again, you cannot conclude that KNN is not at all suitable for a large data problem. I mean, it's really the case by case. If you have some guarantee that the velocity is mild and you have enough distributed nodes to compute the query, and the response time to a query is not so important in your case, then KNN might actually be suitable for your problem. But for example, if you want to deliver a query result, if you want to respond to the query as quickly as you can, then distance computation is kind of really expensive. Plus, even if you're using a distributed computing, you cannot have really, really large distributed nodes that even with the distributed node, each of the node is going to need to compute like 10,000 or 100,000 repeated calculation of the distances, right? I mean, we're talking about millions of rows. Sometimes it can grow much bigger than that, and even if you have thousands of data nodes, you will end up having multiple rows per each of the data nodes. And if you think about it, it is still kind of a large computation. Obviously, it is better than for one computer to do all the heavy lifting, but still, it is going to be a substantial computational load. So you probably don't want to use KNN in those kind of scenarios. So so that's kind of the overview in terms of how applicable KNN is to a large data problem. So I hope the breakout sessions were a good opportunity for you kind of to ponder and think about this issue, because at the end of the day, as a data scientist, in the future you'll need to make this kind of decisions all the time. You have your own problem. What is the best classifier that I can use for this particular problem? You have to make those decisions, and you need to have a high level understanding of what each of the algorithm works and how that can affect the implementation in a big data context. And being able to do that is going to be an important qualification for your job in the future. Okay, so I hope that was helpful. Now I'm going to move on to our next topic. We are actually going to revisit KNN pretty soon, but before that, I wanted to talk about the notion of distances. Okay, so there are many different types of data. So in big data, we talk about documents, a lot of PDF file, web pages, or things like that. You can think about a user table where you have millions of users. You can think about a graph structured data. You can think about image data. If you come to the world of medical imaging, you're talking about thousands of images at one hospital. If you expand that to multiple hospitals, then there are so many different images for different disease and different patients. There can also be a lot of video data. For example, YouTube is they have astronomical amount of videos uploaded by the users all over the world. And for example, YouTube has an algorithm to make a recommendation in terms of what kind of video that, the current user is going to like or not. And, in order to make that kind of decision, you probably want to have some sort of a machine learning model, sitting behind the screen. And then for each of the user, it kind of, does the matchmaking, right? So if you think about that scenario, an ability to process a large quantity of videos and then train a machine learning model and then make a prediction in terms of, what the preference is going to be, is a serious, serious issue over there. You can think of a lot of different time series data and so on and so forth. So if you think about them carefully, measuring how similar they are is a very difficult problem, in fact. So for example, well, since I brought up YouTube, let's talk about YouTube. So, let's say you're launching a video streaming service similar to YouTube, and you want to somehow suggest videos tailored for each individual user. Otherwise, if you just keep suggesting videos that are not so interesting, or, if you're not making any suggestion at all and let the user to explore everything, then, the users are not going to enjoy your service, and then, they'll move away, right? So YouTube, for example, is doing a great job in making those kind of suggestions, right? It throws at you some videos based on your browsing history, right? They throw at you some videos that you may feel interested, and the way that they do it is based on similarity, right? I think the best strategy to make a suggestion on the video is to suggest a video that is similar to what you just watched, because there's a great chance that you want to watch a video with that, similar contents, and there's a greater chance that to entertain you by providing a video that's similar to the one that you already, entertained, you already enjoyed, right? So then, what they're going to do is to collect a record of, which videos you liked, which videos you commented, which videos that you watched for the entire time, as opposed to just watching the first few minutes and then just move away to the other videos. They're going to collect those kind of information, and then, they can easily gather, right, a list of videos that you enjoy the most. So that part is easy. Now then, how would you make a suggestion based off of that list of history, the historical list of videos, and then suggest a new video? So in order to do that, you need to somehow come up with ways to compare similarity between videos, okay? So this is the video that the user liked, and then there are billions of videos, right, in the YouTube database, and you somehow need to compare the distances with those videos and then make a suggestion. So how do you do that? How do you compare videos, right? So that's why defining a distance metric is so important. It is of paramount importance, but in many machine learning literature, they just assume that there's, some distance metric already available. But that's really not the case. In the real life, your job as a data scientist is going to be to, come up with a new distance metric all the time. With that motivation, there are some properties that distance functions need to satisfy. First of all, distance function must be able to compare objects in the data in the notion that is similar to the human notion of similarity. So you want to have distance functions that resembles, the human notion of similarity. If, for example, going back to that YouTube video example, if your distance metric, finds, I don't know, compares a similarity between videos, not based on their contents, but based on, let's say, number of pixels, or, the average RGB color of the pixels, or, something like that, then it's not going to really resemble the human notion of similarity in the context of video recommendation, right? So you can, of course, technically compare, you can measure the distance between two videos by comparing their average pixel intensity. And at the end of the day, you're going to have some number, right? But does that number useful? I don't think so, because that number does not represent the human notion of similarity in the context of video recommendation. So that's the most important criteria, one of the most important criteria for selecting a distance function. Technically speaking, distance functions need to satisfy a certain set of mathematical criteria. Okay, so to have that conversation, we're going to call a data set with the capital letter X, and then the elements of the data set, we're going to use X, Y, and Z. Now, the function, the distance function, mathematically, we're defining a mapping from a pair of data points to a real number, okay? So that's the basic mathematical structure of a distance function. And the properties that the mathematical function d needs to have are as follows. First of all, the distance function has to be non-negative, okay? So the distance between x and y has to be always greater than 0 or equal to 0. Okay, that's the first requirement. And speaking of distance equals to 0, the distance function, the function value between x and the distance function value between x and y is 0 if and only if x is an identical point with y. So only when x equals to y, the distance function can have a value of 0. Or in other words, if the distance function is 0, then there's got to be a guarantee that x equals to 1. So that's another property that a distance function must satisfy. The third property is the symmetry. So it doesn't make sense to have a distance from Chicago to Iowa City be different from the distance from Iowa City to Chicago. So from x to y has to be the same as y to x. If a function does not satisfy that condition, then you cannot call it a distance function. And then finally, this is a triangle inequality. You probably heard about this term. A distance function must possess this property where when you have 3 points, x, y, and z, the distance between x and y has to be smaller than a distance from x to z and the distance from z to y. So what it means is when you take a straight path directly from x to y, it has to be always shorter than taking a detour. So instead of going directly from x to y, if you take a detour from x to z and then z to y, then that detour is going to take more time, right? It is a further distance than the direct shortcut from x to y. And notice this equal sign in this inequality. So when the detour has the same distance with the direct shortcut is only when the point of detour, z, is at the line connecting x and y. So only when z is right in between x and y, you can have this two sides equal to each other. Otherwise, always the detour has a greater distance than the shortcut. So those are the four quantities that a distance function must satisfy. If any of this condition is not satisfied, then you cannot call it a distance function. Okay. Now your job is based on all those properties. You need to come up with a function. Okay. So you need to do two things. One is to find a function that resembles your notion of similarity, and then make sure that the function actually satisfies all these four properties. So that's usually the job of a data scientist. Whenever there's a new problem, unless the definition of the distance is crystal clear from a domain knowledge or from the very definition of data variables, unless the function is given inherently, you need to come up with your own distance function and make sure that the distance function satisfy all these conditions. So that's kind of what we're going to discuss on Thursday. We're going to come back and we're already getting close to 4:45. Get so deeper into stop here. What we can do with the distances and what kind of distances there are, and we're going to see some examples there, and so on and so forth. So thank you guys very much, and I'll see you guys on Thursday.